So you want to understand this summation sign and product sign.
Yes, sir.
So this sign stands for sum, and this sign stands for product or multiplication. So what happens is, if you have to add large number of expressions or numbers, and if there is some symmetricity, for example, if I want to add 1 plus 2 plus 3, all natural numbers up to 100, you know that we can say n stands for natural number. N stands for natural numbers. Then we can replace this summation of n. That means where this is a sum of natural numbers, and then we have to say how many natural numbers. We can say n is equal to 1 to 100. So the starting number is 1 and the last number is n. And when we say n is natural numbers, that means it's 1 plus 2 plus 3. Rather than writing this all complete list of numbers or in this form, this is a compact form of writing it.
Okay.
And this can only work if there is some symmetricity. That is, you can express it. Suppose I want to do 1 plus 3 plus 5 till 101. Okay. Now this is actually, these are what? These are odd numbers. And we can represent odd numbers by this expression 2n minus 1, where
Yes.
n is equal to 1, 2, 3, 4. So if I put the value of n is equal to 1, then the number is 1. If I put the value of n is equal to 2, then the number is 2 multiplied to 4 minus 1, 3. If you put n is equal to 3, then the number is 5. And finally, when you put n is equal to 51, then the number is 2 multiplied by 51 minus 1, that is 102 minus 1, this is 101. Okay. So now what we can do is, we can say it's simply summation of 2n minus 1 and n starts from 1 and n goes to 51, because as soon as I put the value of n is equal to 51, you get 101. Similarly, this was for the arithmetic numbers. If there's an expression, algebraic expression, like x plus y plus z, you can simply write it as summation of x. Or let's say there's a polynomial equation, an x per n plus an minus 1 x per n minus 1 dot 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 a naught. We know that this polynomial equation is of degree n. So we can say it has n roots or n zeros. Okay.
Yes, sir.
So we can say, okay, the n zeros or the n roots of this equation are alpha 1, alpha 2, alpha 3, dot dot dot, alpha n. So as we discussed, I want to find the sum of all the roots. Then write it as alpha 1 plus alpha 2 plus alpha 3 plus dot 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 alpha n. Instead of writing such a big expression, we can also write it as summation of alpha I, where I will take the value from 1 to n. So this is wherever you can find a symmetric expression or addition, you can always use this.
Okay.
Okay. Similarly, if you want to multiply, this multiplication will come very rarely. In our actually in our syllabus, we don't do much of that. So multiply, we only use this one. if it's a product like alpha 1, alpha 2, alpha n, then we can write it as product of alpha I is equal to 1 to n. This is one expression that uses multiple sign, multiplication. Okay. Rest will not come across this sign. More frequently will come with the sigma sign, that is the addition sign. Okay, is this clear?
Yes, sir.
Any other doubt? Okay, so yesterday I gave you that homework, the last question of your exercise. Were you able to solve that question using our?
No, sir.
No. Okay.
No, sir.
So the question was x to the power 5 plus 3x to the power 4 minus 40441118 x cube. Okay, this is a very big number. It's very difficult to factorize it and do all those stuff here. Okay, then there comes another big number 12132362 x square. Again, it's difficult to tackle this number. And then again minus 12132363x minus 2011 square is equal to 0. If you want to find out the roots of this equation, it's very difficult. Okay, but there's a trick here. The trick here is the question says all the roots are integer. All the roots are integers. Okay, so this solves our problem. When it says all the roots are integer, then this is a fifth degree question. So we see alpha 1 plus alpha 2 plus alpha 3 plus alpha 4 plus alpha 5 is equal to 3. Sorry, minus 3. We know that summation of alpha I is minus a to the power n minus 1 upon an. So a to the power n minus 1 is 3 and an is 1 here. And this is actually like a boon for us. The roots will be minus 1, minus 2, plus 1, plus 2, whatever. They're smaller numbers. Okay. But if they're very big number, if the root is very big, let's say minus 100 or minus 101 or whatever, then there's to a counterpart bigger root 101 or something like that. They will cancel each other. So this is something will happen there. So you have to figure out what is that, because the sum is very small. Okay. So when you see at the product, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, this is what product of alpha I is minus 1 to the power n a0 by an. So this is 5. So minus 1 to the power 5, our a0 is this, minus 2011 square upon 1. So the product comes out to 2011 square, which is 2011 multiplied by 2011. And the best part is 2011 is a prime number. So you cannot further factorize it. And since the sum is minus 3, so that both the roots cannot be positive. One has to be negative and another has to be positive. So what we see here is, if this sum is minus 3, I can easily say the roots are minus 1, minus 1, minus 1, which gives the sum minus 3. And the sum of these two has to be 0. So this will be 211. This will be minus 211. And when you multiply all this, plus, minus, plus, and the final product of all this will be 2011 square. So we get the product as 2011 square and the sum is minus 3. So remember, in such question, always a trick will be this number, this A0. which will give the product, will be either a prime number, or even if it's a multiple of prime, the number will be very small, like it can be 2 square into 19 square, something like that, so that you don't get you don't get much factors of this number, and this summation is very small. So whenever you get a prime number here, it will always occur in pair like plus 19 and minus 19, so that this sum becomes 0, this large number. See, the big number can only come here because our an is 1. So these numbers can only come here if this number is very large. So this number is very large. Okay. So this is a trick here. So you can yourself try these questions. Okay. For example, you write this equation: x minus 1, x minus 1, x minus 1, x minus 31, x plus 31. I'm telling you how to proceed. Okay. So this is what 1, 2, 3, 4, 5. And you can write it as x plus 1 also. Okay. So what are the roots are minus 1, plus 1, plus 1, plus 1, 31, minus 31. So the sum of the roots will be plus 2. So this will be x to the power 6 minus 2x power 5. And then you open this. So you'll find the coefficient of x power 4, x power 3, x square, x, and final this constant. Minus, plus, minus, plus, plus. So this will be 31 square. And here there will be big numbers, multiple of 31. Okay. You can take a bigger prime number here. If you wish, you can take a.
How do you get x to the power 6 minus 2x to the power
Pardon?
5? How did you get x to the power 6 minus 2x to the power 5?
Because you multiply x, you get x power.
Oh, okay.
And this diagonal minus 2, I can write it because I already did the sum of the roots. And I know this term will be the negative the sum of the roots. So minus 1 plus 1 plus 1 plus 1 plus 31 minus 31 gives you plus 2. I directly written this.
Yes.
Rest of the number, you have to open it and write an expression for it. But what I'm trying to say you is, you don't give this question. We give us this question, where these numbers are very big, and the students get confused what to do with these numbers. What I am saying is, these numbers are of no concern to us. What matters is the last number and the sum and the first number, because this is 1. So we know all the roots are integers, as the question mentions it. So we just have to worry about the factors of this number. And the factor of this number can be only simplified if I take this number as a prime number. Okay, so that the beauty of this question is 2011 is prime number.
Yes.
Understood?
So, but if it was not prime number, they would only give the small number. They won't give
If it
very
is not
big.
a prime number, then this question is not useful. You cannot solve this question by this trick.
Acha.
All the questions which we solve has some method involved in it. So this question is designed such that we have to take a big prime number here to confuse the student. If he knows this trick of how to solve this question, he can solve it. Otherwise, what will happen is he'll just lost in wondering, okay, how to factorize this number and how to find out the roots and that all. That's all. Okay. So you'll not be able to figure out that plus 2011 and minus 2011 are the roots of this equation. If you doesn't understand that when an is 1 and when all the roots are given are integer, then all the roots will be factor of this number. Is this clear?
Yes, sir.
So if the student has to understand this theorem, which I taught you first time, First day only we did, right? What was the theorem? Rational zero theorem. If there is a polynomial with the integral coefficient, and if p by q, where p and q are relative prime to each other, is a factor of this, is a root of this equation, then p is the divisor of the constant term a naught, and q is the divisor of the leading coefficient a n. Okay, and then it can be simplified. If a n is 1, then if the roots are rational, then the roots have to be integers. So here you are already saying a n is 1, and we are saying that the roots are integers. And from that we start. So we directly have the hint, or the question directly says that the roots are integers. That's the reason we don't worry about other numbers, because plus 3 can be achieved in many ways, or minus 3 can be achieved in many ways. You can always say minus 1.5, minus 1.5 is also minus 3. Okay, but you already argued that the roots are integers. So the roots cannot be rational numbers. The root has to be perfect integers. Okay. So that was the trick here. Any other doubt?
No, sir.
So what do you want me to discuss now? So we have basically covered polynomials. Okay. And I have given you an idea of how to find the roots of a polynomial equation. Okay. Now rest is practice. If you have questions, you can practice those questions. And if you have any doubt on this question, we can discuss it. Now the other algebraic expressions which are very useful when solving the question is x to the power n minus a to the power n is always divisible by x minus a. Is always divisible by x minus a. That is, x to the power n minus a to the power n minus a to the power n is divisible for all values of n. For all values of n. That means either n is even or odd, doesn't matter. For example, you can take the simple example, x square minus a square x minus a, x cube minus a cube, x power 4 minus a4. This is due to x minus a. 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 These are smaller expressions. We actually know the expansion of these expressions. So we can say these are divisible. Okay. So without going into the general proof, I am saying that x per n minus 8 per n is divisible by x minus a for all the values of a. Then x per n minus 8 per n is divisible by x plus a only when n is even. Simply take x minus a. X minus a is not divisible by x plus a. But when you say x square minus a square, it can be factorized as x minus a into x plus a. So now this is
Yes,
divisible by x plus. Similarly, when you do this x cube minus a cube, it can be factorized as x minus a and some expression. But there is nothing like x plus a. The factor of x plus a is not a factor of x cube minus a cube. So this is not divisible by x plus a. Okay. But when you come to x power 4 minus 8 power 4, you can write it as a square minus b square is a square a plus b, a minus b. And this you can further factorize it. So you can get x square plus a square, x minus a, x plus a. So this is divisible by x plus a. So we say x per n minus 8 per n is divisible by x plus a only if n is even. But it is divisible by x minus a for all values of n.
Yes.
Okay. And last in this series is x to power n plus a to power n is divisible by x plus a for n is equal to odd. So you take x plus a, then x plus a is divisible by x plus a. But x square plus a square is not divisible by x plus a. Okay. And you go further, x cube plus a cube is divisible by x plus a. And so we say it is divisible by x plus a only for the n which is odd. Okay.
Yes.
So there are some questions in your sheet which you can solve by using all these divisibility rules. And this is all what is there in your sheet in terms of theory.
So the sheet which you have provided.
Pardon?
So the sheet which you had provided.
Huh?
The PDF which you had given. So from there.
No, no. I'm only talking about you have sent me a PDF file.
Oh, acha, हाँ, yeah,
Whatever I
yes.
have given you, whatever I have given you till now is only covering this PDF file.
Okay.
Basically, depending upon the questions, whatever questions are there, I given you only theory which is supplementing your sheet. Okay. But when I see the types of questions which are there, I don't cover all these questions here in basic algebra. I cover it in a different topic. So I'll tell you how do I cover all those things. So there's another, when we say study algebra, this is basic algebra. And in the algebra, there are other chapters like quadratic equations. Okay. Next chapter is quadratic equation. Quadratic equation is a particular type of algebraic polynomial x square plus ax square plus bx plus c00. So this is a polynomial of second degree. So there are a lot of special formulas for solving this quadratic equation. This equation have two roots. Okay, we call it alpha and beta. So there are many things which will only study under this heading. Okay. Similarly, after quadratic equation, there is another chapter which is known as sequence and series. And you study three types of sequences here. One is AP, arithmetic progression. Another is GP, geometric progression. Another is HP, harmonic progression. Have you done any of this in your
No,
basic
sir.
classes? Have you done this?
No, sir. No, sir. We haven't.
Okay, so you have not done this. Okay. So once you learn all these series, then only you will be able to do some questions which are in your sheet. Otherwise, you cannot do it. So under this sequence and series topic, there comes a term known as telescopic sum. Okay, where we are given a sequence is numbers or something like that in a particular order. Okay, and we have to find the sum of all the numbers. For example, we have to find 1 plus 2 plus 3 plus 99. Okay, or we have to find 2 plus 4 plus 8 plus 16 plus 96. Okay, something. So this is this arithmetic progression, this is geometric progression, and harmonic progression is something special. So when you have to do all these things, there are formulas for this. And in that, the last topic is telescopic sum. So some formulas which are given here is 1 upon k multiplied by k plus 1. If I want to find the sum of these numbers, that means k is equal to, let's say, 1 to 5. What does this mean? This is 1 into 2 plus 2 into 3 plus 3 into 4 plus 4 into 5 And sometimes the series may become difficult also. We may require these formulas to solve it. So, but because it is given here, I'll tell you, I can write half as 1 minus half. 1 by 2 into 3 can be written as 1 by 2 minus 1 by 3. This is 3 minus 2 by 3 into 2. Okay. So basically what is happening here is all the numbers are 3 into 4, 4 into 5, 5 into 6, k multiplied by k plus 1. So this can always be written as 1 upon k minus 1 upon k plus 1. So what benefits we get here is every time the next number which comes is a negative of the previous number and they
So we
cancel
can cancel.
and they cancel them.
Yes.
Suppose 1 by 1 into 2 plus 1 by 2 into 3 plus 1 by 3 into 4 plus 1 by 4 into 5. So this can be written as 1 minus half plus 1 by 2 minus 1 by 3, 1 by 3 minus 1 by 4. What you see here is this will go, this will go, this will go, this will go. Last term and the first term are remaining. 1 minus is 5 by 6. So what he has done is he is simply saying that 1 upon k into k plus 1 is 1 upon k minus 1 upon k plus 1. So when you expand it on this formula, 1 upon k minus, what we see is in between all the terms cancel out. The first term for k and the last term for k plus 1 will remain. Okay?
Yes, sir.
Then if I say 1 upon k into k plus m, what will happen is if I say 1 upon k minus 1 upon k plus m, then this will be k plus m minus k divided by k into k plus m. So this is equal to m upon k into k plus m. But here m is coming, there was no m here. So what we do is we divide by m. We divide by m. So here we divide by m. So 1 upon k and 1 upon k plus m can be written as 1 upon m, 1 upon k minus 1 upon k plus m. Is this clear?
Yes.
Hmm?
Oh, yes, sir. It's fine.
So the last formula which is given here is 1 upon k, k plus 1, k plus 2. So what do you think? What can we do? Any idea?
Yes, sir.
No idea. So, okay. So let me look at like this. I'm trying to find out the result. Okay. So let us take this one and let us take like this. What will happen? 1 upon k into 1 upon k plus 1 can be written as 1 upon k minus 1 upon k plus 1. And 1 upon k plus 1 multiplied by k plus 2 can be written as 1 upon k plus 1 minus 1 upon k plus 2. Right? I can write it like this.
So how do you get 1 upon k plus 1 minus 1 upon k plus 2?
So this is simple from here only, no? Instead of k, you
Oh,
write
okay.
k plus 1. And so you write here k plus 2. These two numbers are just
Okay.
difference of 1, no?
Yes.
Okay. But I want this. So if I add this, what will happen is these two will cancel out. If I add this, these two will cancel out.
So it's 1 by k minus 1 by k plus 2.
But we'll not get this expression. If I subtract this, what will happen? 1 upon k into k plus 1 minus 1 upon k plus 1 into k plus 2. So this will be 1 upon k minus 2 upon k plus 1 plus 1 upon k plus 2. What will we get here? We'll get here k multiplied by k plus 1 multiplied by k plus 2, k plus 2 minus k. Okay. So here what you are getting is you get 2 divided by k into k plus 1 into k plus 2. But we are not interested in this 2. That means we have to divide this expression by 2. If we divide this expression by 2, we'll actually get this expression. So what we can do is we just divide this by 2.
Okay.
Okay. Get it?
Yes, sir. So for questions, let's say they give a unique pattern, do we have to derive the formula for that? Do we just have to memorize the pre-existing formulas and apply it in the question?
Okay. This pre-RMO is nothing that you have to remember a formula and apply it. It is not a paper of that kind.
Okay.
These are some standard techniques which can be used, but they will be the part of your tool. Okay. They are not the direct application of the formula. So you have to go beyond these formulas when you are solving pre-RMO questions.
Okay, sir.
So this time what is happening is, I think there are around 24 questions. Starting 10 questions will be of 2 marks. Then there are few questions of 3 marks, and there are few questions of 10 marks, or either 5 marks or 3 marks. So these 2 marks question will be easy. Okay. You can say more or less there will be direct application of formula. But this question will be medium to difficult. And this 10 mark question will be very difficult. Okay. These questions will not have any direct application of formula. Okay.
Okay, sir.
Formulas will be there, but after using that formula, you may have to do a lot of manipulations. Mostly the bigger questions in pre-RMO, like 10 marks questions, or they will be always case based. I'll give you some examples after 2 or 3 class, that what if case 1, what if case 2, what if case 3, what is case 4. Okay. At some point of time, after application of formulas, we'll get stuck. And there is no direct formula which can solve the question further. Then it can only be, you can only do some analysis and find out some symmetric or some way to branch out the question under different categories and different cases, and then you have to solve the question. Okay.
Yes.
So these questions are very difficult, and these are right now not our cup of tea. Because you are right now in which class? 10th class, 9th class,
Ninth.
9th class. This is something when you have finished your 10th class syllabus and you have some exposure to 11th class mathematics, then only we can go for these questions. Okay. But what we can do is, once we do some simple, once we finish one topic, we can go into the depth of that topic and try to see that whether we can solve a 10-mark question of that particular topic. Okay.
Yes.
So what we'll do is, once we finish this complete algebra in whatever time frame, we can go and try some big, some past year problems of pre-RMO, which were actually of 10
Yes.
marks type, and see how much depth we have. Those solutions will be around 1 page or 1.5 page, and lot of mathematics, lot of arithmetic, and lot of logics. Okay, not direct application of formula.
Sir, in PRMO, is it all objective or are there some subjective questions as well?
I don't know. This time they are saying when there will be 10 marks question. I doubt it will be objective. 10 marks question has to be always subjective.
Yes.
2 marks question should be definitely objective. Even if a 10 marks question is objective, the solution will be very, very lengthy. You cannot simply guess it and get the answer. It will be very difficult. Okay. Okay. So we over the class here only. And I asked you to send me your doubts. I've not received any doubts from you.
Yes, sir. Sir, I have actually compiled doubts. I'll send it in sometime.
Because see, Sanvi, this class will be helpful to you if I really solve your doubts. Because teaching
Yes, sir.
theory and teaching 1 or 2 examples is not going to give us depth here.
Yes, sir.
To actually get the depth of the subject, we need to solve some problems, and the problems has to come from you, right?
Yes, sir. Yes, sir.
Okay, tomorrow is
Then,
Rakhi. What about tomorrow?
sir, I can attend tomorrow.
Okay, fine. I'll let you know if there is a holiday here, then I'll let you know about the holiday.
Okay.
Else we'll have the class, okay?
Okay, sir.
Okay, we'll hold the class.
Okay.
Bye bye.
Thank you, sir. Bye.
Bye.